introduction, Rohan has introduced our architecture and our compiler. Oh, by the way, can the people in the back hear me? Okay, very cool. Yeah, they have introduced our architecture, our compiler, and now with my talk, I want to give more concrete examples on how we think our group we leverage our GeneSys architecture to facilitate our latest research. And also we want to use these two examples to showcase some of the features and the infrastructure we provide with GeneSys and build for GeneSys, so that if you guys are interested, you can actually use the GeneSys platform for whatever your research will be. All right, something about a little bit about myself. I'm a third-year PhD here at UCSD. I am the co-author of the tandem process paper. I helped Suresh with some microarchitecture, and I did the implementation for tandem processor on RTL. Putting it up FPGA and wrote the software simulator alongside with other collaborators. My research interest is in cross-domain acceleration and robotics and AR/VR applications. All right, so for the very last time, end-to-end applications and not just neural networks. I know we've been saying that for the entire 2 days. So two examples here will be on opposite side of the spectrum. With the first one is the data center application, which is a video surveillance application that you have video decoding and ingestion, you have object detection, and finally you have data analytics. The other spectrum of the application, you have edge applications. In this case, we're thinking about a closed-loop brain modulation application, which involves digital signal processing, such as FFT. You have data analytic, so like some classic machine learning, and you also run like deep learning, sometimes hopefully reinforcement learning, and finally do some model predictive controls. Yeah, so let's look into the cloud. Imagine the first. Imagine we map the very first example I talked about to a multi-acceleration system, where the video application is offloaded. A video kernel is offloaded to a video codec accelerator. The DNN portion is accelerated to a offloaded to a DNN accelerator, and the data analytic kernel is offloaded to data analytics accelerator. Even though we are able to achieve like significant result improvement with the compute, the data motion in a multi-acceleration system actually becomes a bottleneck. In here, we define data motion as both the data movement and the data restructuring. And the core cost of data motion overhead is because data restructuring kernels are actually executed in the CPU. So you will have to copy data back and forth, and you also have to do the restructuring computations. Yeah, so in our HBCA paper, we actually look at this problem. This is actually have two sides of this problem. One is where do you place the accelerator to on the entire system stack to offload this computation kernel from the CPU. And the other side is how do you design such accelerator so that it actually maps well with the data restructuring kernel. And luckily, over here, if you look at the data restructuring kernel that's happening, it's mostly like the non-gen layers in neural networks. They are like very low data reuse, and they're usually very well vectorized and pretty much processed in a streaming fashion. So in this case, GeneSys actually lends itself very well, especially the tandem processor, to tackle this challenge. So basically, we designed this DRX hardware prototype with the GeneSys framework. So I remember somebody asked if we can delete stuff. So basically, we just went into the RTL and delete a bunch of stuff that is never used in this specific workload, and we add specific ops such as cast, concatenation, etc. That happens a lot inside the data motion application, inside data motion kernels to become the specific accelerator for data motion. And of course, as Chris mentioned, every time you make some changes of the new, add a new hardware unit or hardware operations, you have to make the corresponding change in the software. So this, so by doing this, this will allow us to quickly prototype and advance our research, as well as we can obtain some very accurate benchmark numbers, because we can actually run this on FPGA, and since our FPGA have like pretty much solid memory interfaces, those numbers, both the performance numbers as well as the memory numbers are very accurate. So that's the DMX work, which showcases how we use GeneSys power generation to facilitate our research effort in systems. Now let's look at an application on the other side, which is the ultra-low power neuromodulation workflow. And along with our neuroscience collaborators at Emory University, we're building an end-to-end prototype deep brain modulation system that has the potential to treat a wide range of neurological and psychological disorders. So as shown in these figures, this is a typical workload for a close to neuromodulation. And these neuromodulation workload usually consists of kernels from multiple domains, including digital signal processing, data analytics, and you can see the control network and the model network, which utilize MPC and reinforcement learning. So besides the cross-domain nature of such workload, we also are facing low power constraints. As Rohan mentioned before, in the brain environment, you only have pretty much a power budget about 12 milliwatts to 15 milliwatts. So in this case, we leverage GeneSys configurability and also programmability to both reduce the hardware energy consumption, as well as to implement quantization through mostly software compiler implementation to achieve quantization. And I will walk through how we actually did quantization on the GeneSys. And the last part is, this is actually a multidisciplinary research. We actually work with several neuroscientists, PhDs. And usability and barrier of entry is actually a very significant barrier in this case, because we actually speak totally different languages. We have some communication issues during the collaboration, as well as, of course, we're one research group is doing neuroscience, and the other research group is still doing domain-specific computation. So the gap there is very wide, and we want to reduce this gap so that we can serve our collaborator better. Yeah, so to tackle the end-to-end cross-domain acceleration problem, I'm not going to go into deep details. So basically, we already introduced this multi-topic compiler and this programmable domain-specific accelerator. That's our plan for the future. We're investing heavily on this direction. But for the low-power design, the first approach we took is to leverage the configurability of GeneSys because it's fully parameterized. So in the neuromodulation workflow, which utilizes an ultra low power version of our GeneSys chip, we actually implement a 4x4 configuration for systolic array, and for tandem processor we do a 4-link tandem processor. And for Sarush and Rohan's paper on high performance, when performance matters, we just scale up the configuration and evaluate the design, basically 32 by 32, 64 by 64 configuration. And it's worth mentioning that we have verified 4 of these configurations on FPGA, so it's pretty much the parameterization is very mature, and you can configure the PE size, the buffer size, and the communication interface bandwidth in this config file, which is outlined in here. Okay, so far any questions? All right, the next section I want to talk about how we do quantization to save more energy in this new modulation version of the GeneSys. So let's start with some basic for quantization. So here we're specifically talking about integer quantization, which is a mapping between a real number and an integer number with a scale and a 0 point. It's pretty simple conceptually. It gets very complex once you dig into it. And the second figure on the right is actually from this Eichler paper, which I found is extremely helpful to understand quantization, and they make a perfect figure for quantization. And so there's two types of quantization. The first type is called simulated quantization. Sometimes it's called fake quantization, which is the idea is just to perform the computation in floating point, but when you do the communication, you quantize the result or the input of these models to save only communication. And that's the quantization method on the most left. I think that's how the media GPU does it initially. In the middle is a more advanced fake quantization, which is you do the matrix multiplication in tape, but you do the non-gen operation in floating point 32. And on the most right is how Eichler do their quantization, and it's like real quantization because everything is happening in int A. But the trade-off for this approach is that they have to specifically implement like integer A version of non-gen operation. Basically, they have to utilize approximation, rounding average to do the exponent, softmax, all those non-gen operation. Yeah. So for GeneSys, we actually support both the middle and the middle simulate fake quantization as well as the real quantization. So you can, as you can see here, that's exactly how we are doing the quantization in GeneSys. So on the left, we're doing the int8 linear layers. Before we start going that deep, this here is just a very simple example of a linear layer plus a redo activation. So we do the matrix multiplication in 8 as our current systolic array implementation is mostly in 8. And the resulting number will be an int32 number. And we do the dequantization layer. We do the dequantization on tandem processor, which convert the int32 into a floating point, into a fixed point 32 number. And we do the redo in the fixed point number. Then after that, we quantize the fixed point 32 number back to an int8 number, and either proceed with the next layer or store it back to memory. How a real quantization will happen on GeneSys is that you just do linear and redo with int32, but you have to cast the redo output back to an int8 for the next layer. Any questions so far? Yeah, so that's how, so in order to achieve these models, we have to make change to both the hardware as well as the compiler. So this is the same code that Chris showed before, it's redo, but on the right side it has the quantized redo version. So there's only a few changes that you have to make here. So first one, you have to config the data type for quantization, because we're switching between either fixed point 32 to int32 or to int8, or we are switching between int32 and int8. You have to specify the target of your quantization, specifically the data type of it. And then you're going to save some of your quantization parameters, which is your scaling number and the 0 point. And at the end, you can see those are dequantization and quantization ops specifically for the use case on the left. So for dequantization, you do a left shift and you multiply by the scale, and for quantization, you do a multiply with the scale and then cast it to int8, which the specific casting mechanism is the data type that you use in the cast is specified at the very beginning. Does this make sense? All right, going forward. So the change in hardware is you can either implement the non-gen layer in ALU with specialized module as solution, was saying like you can either go with hardware implementation of higher order, like more significant modules, such as he gave an example of Sigmoid, or you can implement it in compiler with primitive mass building blocks. So in our implementation, take softmax example, we pretty much implement the approach that I would take, which is decompose softmax into primitive operation, and we implement that in the compiler, and it just compile and runs on our hardware. So there's no hardware change, but I think I have read a lot of literature where you just introduce a softmax module on the hardware. That will also works on our hardware. To insert the softmax instruction in the compiler. All right, so that's how we solve that's how we tackle the low power requirement for this neuromodulation workflow. So the last part is, so as I mentioned before, there's a significant barrier of entry for interdisciplinary research. So computer science, computer architecture PhD students have to basically handle all these complexities in power, as well as in power and embedded system, as well as in compilers. But for neuroscience PhD students, they do a bunch of important science that I never understand. But as far as I can concern, they only use Python to implement their models and train and do inference. So why not we just provide them with Python APIs and hide all these complexity to ourselves, and just give them simple CUDA-like, OpenCL-like interface, so that you can just use it with other libraries, because neuroscientists actually use a lot of libraries for their reinforcement learning models. Yeah, so that's our GeneSys Python API. It's very simple. It's all encapsulated. It has the initialize, pretty much preparing all the files, preparing the hardware, the synthesized hardware, and put it on the FPGA. So this is in context of the FPGA, by the way. And it has run, it has check output, which compare the golden output to the output of the FPGA, and it has performance data. It can plot the data too. Yeah, so this is actually the Python API is part of our development infrastructure that also include performance profiling as well as verification. For performance profiling, we both provide hardware performance counter that is synthesizable to the design. So at each compute unit and each in-memory interface, we have a PC module. And at the end of the execution, PC module will record their collection to the PC top module, and the top module will copy back. Will send the performance data through the same interface where it gets the instruction. And we support text-based output, or we can plot the output with Python API. We also have a software simulator that is based on Python. It is really fast because it can actually take some time to get the hardware running. So if you don't want to go through that and all your research is only in compiler, you don't really need to set it up. So you can use this software simulator. It simulates the compute units. So it has the cycle counts for compute times in both compute unit. It supports the software pipelining, so it models that. So it's when the layers are fused and tiled, it still gives pretty much accurate results. And it also supports memory energy moduling through check time. The input to this software simulator is exactly the same as the input to the hardware itself. So the hardware configuration file is also shared between this software simulator and the actual hardware. And the output will be the performance stats, the energy stats, and the visualization. So the first version of this simulator was hitting around 10% error rate. The main error is coming from the memory interface, which is more out of our control because we have to compile with the AXI interface, and sometimes those can be a little bit hard to model. But we keep updating our simulators, and right now for ResNet 50 we're around 1% difference than compared to the actual FPGA. And we're going to continue improving our software simulator because we're actively adding new stuff to GeneSys. And as far for hardware designers, this is traditional RTL test bench. It uses Xilinx, the useful model AXI verification IP. So the memory interface is completely, you can verify your change in memory interface. For example, when you change the bandwidth of the memory interface, it could cause some bugs, or you want to implement a more efficient version of it. It also has golden output comparison, and these are the files to configure this RTL test bench. Finally, we also have OpenCL-based hardware emulation. So this is triggered by the host CPU, and it's identical. The steps are identical to how you would run a real inference on an FPGA. So it's kind of like a last step test before you actually run everything. So we verify the host driver interaction, and the good thing about like running this compared to running something directly on FPGA and finger crossed hopefully it works, is that this has the waveform. So if it doesn't work, you can use the waveform to debug instead of inserting LA, which is very, very time consuming to do. And this is located at this address, this folder, and the GeneSys Architecture folder is also access control, as Chris mentioned. So if you want to take a look and utilize the compiler, just apply it as he told. Yeah, so with this verification infrastructure, we can actually achieve, we actually achieve like we successfully synthesized both FPGA version of our GeneSys, and as well as successfully taking out on the 12nm technical. And worth mentioning, it is also available on AWS. We also have a tutorial, step-by-step guide on how to bring it up on the AWS F1 instance, so that you don't really need to own FPGA to check our stuff out. Yeah, so that's the end of my talk. So this is GeneSys. Hopefully you enjoyed the tutorial, and we're very open to collaborations, and hopefully our work can facilitate your research, and we will be